Welcome to The Explainer. We're about to dive into an idea that could completely flip the script on one of our biggest global challenges, and maybe even change how we think about the very air around us.
All right, so let's just start with a really provocative question, one that kind of shakes up a core belief most of us have.
You know, for decades, we've been trained to see all this excess heat in our atmosphere as a danger, right? A problem we have to fix. But what if we've been looking at this completely backwards? What if all that heat wasn't a liability, but was actually an asset? And that is the huge paradigm shift we're talking about today. It's moving from this column on the left, heat as a problem, a driver of instability, something to get rid of, over to the column on the right, where it's seen as a global resource, a vast, untapped source of continuous power. Something not to mitigate, but to actually harvest.
Okay, so how on earth is that even possible? Well, to get it, we have to look at our atmosphere from a real first principles physics point of view. Think of it like a giant planetary-scale heat engine.
It all starts with a simple, basic fact of physics. The air, all around us, right now, contains a colossal amount of thermal energy. We're basically living inside a giant reservoir of heat. But here's the key, and this is really the whole secret. That energy is not spread out evenly. And in physics, whenever you have a difference, a gradient, whether it's pressure or voltage, or in this case, temperature, that's an opportunity. That's where you can get work done. So down here, near the Earth's surface where we live, it's relatively warm, right? The sun's been heating it up. This is our hot side. In physics terms, that's roughly 300 Kelvin. We'll call it T1. And then as you go up, way up into the upper atmosphere, it gets significantly colder. Dramatically colder. And that gives us our cold side, our T2, which is sitting at around 250 Kelvin. So what you have is this constant, reliable, and really powerful temperature difference of about 50 Kelvin, or 50 degrees Celsius if you prefer. That's a huge, natural, and persistent gap. Now, this difference has a name. It's called the thermal gradient. And it's not some small thing. It's the engine that literally drives all of our planet's weather systems. It's a massive heat engine, always running. And until now, we've only ever experienced its effects as, well, weather.
So, okay, we have this constant flow of heat, always trying to move from the warm surface up to the cold sky. The big question then is, can we get in the middle of that flow? Can we actually tap into it?
The question is, how do you actually convert that natural flow into useful, continuous power? Well, the process for doing it is, honestly, pretty elegant. It basically comes down to 3 steps.
Okay, step 1, you capture. You use special, advanced materials to grab that natural heat flow right out of the air. Step 2, you convert. You turn that heat energy directly into DC electrical current. And finally, step 3, transmit. You transform that electricity into microwaves and beam it down as focused energy.
Let's move on and see how this all builds up. This idea, this direct conversion, it's so fundamental that it really puts atmospheric thermal conversion, or ATC, into a very special class of scientific breakthroughs.
To really get the scale of this, you have to think about the other great energy conversions in history. Back in 1938, we figured out nuclear fission, how to turn mass into energy. Then, in 1954, we got the photovoltaic cell, which turns light directly into electricity, and that brings us to today, with atmospheric thermal conversion, the ability to harvest the thermal energy of the atmosphere itself.
But beyond just being a cool new idea, what makes this new asset truly revolutionary is its environmental profile. So let's look at the numbers. How does it actually stack up?
Now, this is really interesting. If you look at the entire life cycle, from cradle to grave, coal pumps out 935 grams of CO2 equivalents for every kilowatt hour. Solar panels, a fantastic clean tech, are way better at 45. But look at ATC. It's projected to come in at just 13. That is an incredibly small footprint.
And this chart just makes it crystal clear. Look at that difference. It puts ATC in a league with the absolute cleanest energy sources humanity has ever come up with, right up there with wind and nuclear.
So why does any of this matter? Well, this isn't just some abstract theory.
it has real, tangible applications that can turn a local problem into a local solution.
Think about the urban heat island effect, for example. You know how cities get so dangerously hot? With this tech, that excess heat, which is a huge liability, could be harvested directly. So you're simultaneously cooling the city center while providing resilient 24/7 power. We're talking about a single unit powering hundreds of rural homes or avoiding tons and tons of CO2 emissions every year.
This quote just says it all, really. The technology represents the transmutation of a global liability into a primary, useful, and exportable energy asset. We're not just putting a Band-Aid on a problem here. We're literally creating value from something we used to see as waste.
This really makes you stop and think, doesn't it? It forces us to reevaluate what we even consider a resource versus what we consider waste. I mean, if we can learn to harvest the sky itself for clean, continuous energy, what's next? What other massive challenges out there are just opportunities in disguise?
That's all for this explainer. Join us next time as we break down another complex topic.